The mission of Team On Our Last Nerve is to remove the permanent prognosis associated with central nerve system injuries. These injuries include traumatic brain injuries, such as the one sustained by my Aunt Julie, my godmother. These traumatic brain injuries occur in over
1.7 million
people a year in the United States alone, and spinal cord injuries occur in 12,000 people annually in the US. We decided to look at spinal cord injuries because these injuries are more similar to peripheral nerve system repairs, which are currently done, and we propose that by using similar methods, we can design a spinal nerve patch that will help with lacerations, contusions, and cavities, which make up 70% of all spinal cord injuries. We hope that by using this patch, we can facilitate nerve repair and eliminate paralysis and limited functionality for many of these patients.
Now I'm going to talk about our polymer selection. We initially considered several different biocompatible polymers such as PCl, PHEMA, and PGS. Ultimately, we settled on PEG, PEG, polyethylene glycol, a material that has been previously used in the tissue engineering and biomaterials lab. We selected a 4-arm PEG acrylate because we thought that the 4 functional groups would contribute to network formation in our hydrogel. We also selected PEG because of its affordability, high biocompatibility, and considerable mechanical properties.
So after we selected our polymer, the 4-arm PEG acrylate, we also had to look into photo initiator, and we selected our Cure 2959 because of the fact that it's water soluble and is often used with PEG. Some degree of cross-linking tests were conducted, and we optimized the formulations of this mixture so that we had 2 different combinations of 15% and 20% PEG and 0.05% Ergocure, as well as 5% gelatin. And the gelatin's in there so that the material is viscous enough so that it can print.
In addition to the chemical considerations, we also had several design parameters that we needed to consider in making our design. The first one, that our patch would match the inner spinal curvature of the nerve bundle and it would fit within the inner spinal canal. In addition, our porosity needed to be tailored to block out macrophages and biological inhibitors, and we tailored that through our cross-linking density. The third, printability, has to do with the viscosity of the printer feed, and that has to do with the concentration of polymer in our hydrogel feed. And finally, biocompatibility has to do with the polymer that we chose and the Ergocure photo initiator that Jack talked about with our polymer chemistry.
Gel permeation chromatography was used successfully to confirm the 20 kilodalton molecular weight of our PEG samples. I'm going to explain dynamic mechanical analysis, or DMA, which was used to get stress-strain curves and therefore the compressive modulus of our hydrogel samples. First, we cross-linked the samples in 96 well plates in the UV box for varying amounts of time. We then removed the samples from the 96 well plate and cut off the menisci before loading them into the sample. We found that our samples had an average compressive modulus of 636 kilopascals and an average failure stress of 55 kilopascals.
Dynamic scanning calorimetry is used to measure the several different transition temperatures for polymers.
For this characterization experiment, the conditions used for the 6 samples in the hydrogel swelling test were replicated to prepare the DSC samples.
The DSC thermographs produced by our 6 samples are shown. The crystallization temperature of each sample is the minimum of each peak produced, as shown with the arrow. In each thermograph, the crystallization temperature was well above the average body temperature, which is around 37 degrees Celsius, and a highly deadly fever is around 41 degrees Celsius. Furthermore, the lowest crystallization temperature from our samples was around 51 degrees Celsius with a 20% PEG at 1.5 minute exposure. The crystallization temperature is relevant to our project because we don't want the hydrogels to soften inside the body in case a person has a fever. The peaks start forming at around 42 degrees Celsius, which is still above a deadly fever temperature.
Degradation testing was conducted in order to determine the rate at which our polymer would be hydrolyzed within the body. To do this, we measured mass loss over a period of time when the polymer was subjected to body-like conditions.
Okay, so I'm going to go over how we did our hydrogel swell test, and that was in order to determine the cross-linking density of our polymer matrix. Using this equation, we were able to figure out the cross-linking density, where V sub R is the volume fraction of the polymer in the swollen gel, and V sub S is the molar volume of the polymer. And then chi is figured out from the Bristol-Watson equation here. In order to perform our hydrogel swell test, we took 6 samples, 3 of 15% PEG and 3 with 20% PEG, and we used different exposure times of 1.5 minutes, 2.5 minutes, and 5 minutes to test how they affected the cross-linking. Samples were hydrated in DI water for 24 hours, weighed, and then they were placed into a litholyzer where they were dehydrated for 72 hours and then re-weighed. As you can see, the percent loss of water is listed here. And this was used to figure out the cross-linking density. The highest cross-linking density was determined at 5-minute UV exposure for 50% and 5-minute for 20%.
We supplemented our in-lab techniques with computational modeling in the form of finite element analysis. We created a 3D model of the sheath here using material properties yielded from DMA. Running this model, we deformed the sheath to the maximum radius of curvature of the human spine, or 30 centimeters. Examining the model, we can see that the von Mises stresses are concentrated on the outermost suture hole, and they're exorbitantly larger than the compressive failure stress yielded in DMA. This led us to conclude that our model would be best suited for a patient that is stationary during recovery.
Due to unforeseen circumstances, including the malfunctioning of our 3D bioplotter and the thermomechanical analyzer, or TMA machine, being offline, we were unable to complete all of our initial design objectives. However, we did complete extensive hydrogel characterization, including studies of cross-link density, compressive modulus, stress at failure, porosity, degradation time, and the effect of sutures on installation. These data and experiments show that successfully printing a nerve patch is possible. In the future, we would like to revisit printing to see if we can achieve a successful prototype using our pioneered PEG-TUB blend. We would also like to conduct increased characterization in the areas of cell viability, gelation and viscosity, as well as TMA testing at body temperature, or 37 degrees Celsius.
Thank